So the graphing relationships, we're starting a chapter on functions, and we'll be talking more about what functions are as we get into the chapter. But want to start out just with this comment here, that time is pretty much always going to be on the x-axis. So we have the independent variable goes on the x-axis, dependent on y. And pretty much always things depend on time if you have time in the problem. So that's the first line. Time is pretty much always on the x-axis. And so for the second part, if you're interpreting a graph, kind of the key to figuring out graphs, and this is big in a lot of the standardized tests, is they give you a whole bunch of graphs and then you try to interpret the data. I would encourage you to, as you look at a graph, look at what's happening to the y value, what's happening to the height as you go to the right. So look at what happens to y as you go right across the graph. So the first one, the y value stays, yeah, I probably shouldn't have said stays, but y stays the same. So if this were a distance versus time graph, and you don't have to put the d and the t on, but time would be on the x-axis, distance would be on the y-axis, so the distance stays the same, so the object isn't moving. You know, that the distance away stays constant as time goes by. If you have this next one, the solid blue line here, y is going up, going down. Fast or slow? Slow. So I have like y increases slowly. And then I have that dashed one, which for the dashed one, y is increasing faster or slower? Faster. So I'm going to do like a quickly and like dashed lines. Pretty sweet, huh? Yeah, longer than I thought. And I can't do y's with dashes. Apparently, that didn't work with it too. But okay. The last, are you with me? If it's steeper, the change is happening faster. That after a certain amount of time goes by, you know, y has changed more here than there. All right, last one. Y is decreases. So if these last two are also distance versus time graphs, for that very last one, the distance is getting smaller as time goes on, so the object is getting further away or closer to you? Yep, so this would be an object's getting closer to you, and eventually the distance would be 0. It hit the x-axis, then it would be to you. Here the object's going away slowly, here it's going away faster. So, good. For these next two, if you were to have something like this here, so that would be like, the shape doesn't really matter. The point is it's all one connected thing. So that's a continuous graph. And graphs are supposed to be made up of points. So in other words, like all these points are now like touching each other. A continuous graph, you don't have to lift pencil. So don't have to lift your pencil. And really for those continuous graphs, what we're trying to say is, if you're talking about these x values, x could be anything. Could be a decimal, could be a fraction, could be like natural numbers like 1, 2, 3, 4, 5. But x could be anything. Where if instead you were to have a graph of points, oops, didn't mean to hit that button. Instead, if you were to have a graph of points, and the shape doesn't really matter, but I'm just going to put some dots on there. I'll have mine going up, and maybe I'll change direction, have them coming down. But that's going to be called a discrete graph. In a discrete graph, it's going to be unconnected points. Or you could, if you wanted to, say, you must lift your pencil. And you're going to get those discrete graphs when x couldn't be certain numbers. So maybe x could only be whole numbers. Or x could only be like whole numbers or halves or something like that. But one final graph or one final example in a graph, and then we're done. So Henry sells cars. He makes $20,000 a year and $500 for each car sold. Totally made this up. I don't know how close this is to real life. But graph Henry's salary is a function of the number of cars sold. So for our friend Henry, I'm going to say like 0 and then just put in like a 1, 2, 3, 4, 5. So something like that. You could label all those dashes. You could just label some of them. You guys remember doing broken axes last year? So I'm going to put in like one of the little broken axes and then put in a $20,000 here. And then you could do a higher one if you wanted to, 25,000. Then you could put in different things. The really point I'm trying to make for this here is which type of graph is it going to look like? Is it going to be continuous or discrete? Discrete. Because Henry, unless he's working at a junkyard, you agree his boss isn't going to like it if he sells like partial cars? So, well, I sold just the engine out of this one, so I want like half of my $500. And it's like, that's not going to work, you know, or yeah, it just needs the bumper. I sold him the bumper. You got $100, you know. So for this here, we could at least accurately put the point without too much difficulty there. If he sells 0 cars, he makes $20,000. Just sits in the office all year, collects his 20 grand, playing solitaire, or whatever video games they have. But if he sells 1 car, then it's going to be 20,500. So then you could put a dot up a little bit. I'm kind of being a little bit liberal with where I'm putting it height-wise. But if he sells 2 cars, okay. The dot should be in a straight line, though, right? So I'm realizing I really should have just deleted this off the top, because I'm not going to be anywhere correct with that. But the point is, at least, we should have a graph of dots, and those dots should be going up at a constant rate, because every time he sells 1 more car, he makes $500 more. Fair enough? So it's a discrete graph. It's made up of points, so you can't sell part of a car and get a commission. And it should be linear. It should be going in a straight line.